Hi, so this is our presentation on torrefied biomass. I'm James Washington, and let me begin. So, what is torrefied biomass? We all know that biomass is a renewable source of energy that comes from plants and animals. Torrefied biomass is simply biomass that has gone through thermochemical conversion in order to possess more favorable combustion characteristics. Biomass goes from having wood-like qualities to having coal-like qualities after the conversion process. This altered fuel needs less energy to grind it down to a desirable size and can be stored long term. This process results in a 30% decrease in mass, but keeps 90% of the energy content stored in biomass. Pictured is different variety of biomass samples that went through the torrefaction process. The history of torrefaction has dated back all the way to the early 20th century. In the 1930s, heat treatment of wood was done to enhance favorable properties to when it began. This process began to develop even more in the 1980s when the reactor designs were patented. But torrefaction really began to evolve in the 21st century when better technology was introduced, which allowed for a rapid increase in research and development of torrefied biomass. Biomass goes through torrefaction to change its physical properties, and it provides a much better fuel quality for combustion and gasification applications that biomass is often applied to. This process occurs at 200 to 300 degrees Celsius with the absence of oxygen. Torrefaction, also known as a form of pyrolysis, removes all of the moisture content from biomass in order to increase calorific value. Water is known to impede biomass from having a higher calorific value, and that is why it is removed. Torrefaction also removes much of the volatile content that biomass contains, such as carbon monoxide, carbon dioxide, hydrogen, and methane content. The result of torrefaction is coal-like biomass that cannot rot and is much lower in mass than the untreated biomass. This is the torrefaction process. It begins by feeding the untreated biomass into the reactor, where it will be dried and lose all of its moisture content right here. The flue gas is then exited through there as it goes on to the torrefaction step. This initiates the carbonization process. Torrefaction gas is repressured and heated before it is recycled to the reactor. The moisture content of the feedstock in this process is extremely important since the feedstock property determines the required heat demand. The biomass is then cooled, and then the product is torrefied biomass itself. lesser in weight and slightly lesser in energy content. The targeted biomass structures in torrefaction are cellulose, hemicellulose, and lignin. As you can see from this picture, biomass is preheated to break these structures down to begin the process of torrefaction. The entire mechanism can be split into three subjects: depolymerization, where the shortening of large molecules take place, which is driven by the high temperature of this process; devolatilization, where the organic volatiles in biomass are removed; and then lastly, carbonization, which I mentioned earlier, but where the carbon content in this mass is concentrated. The uses and applications of torrefied biomass. Torrefied biomass has very similar qualities of coal, so it is not a surprise that it is often used as an alternative to coal in order to reduce unfavorable emissions, but at a cost, has a lower energy content. It could replace coal in the electricity production and also steel production. It's also an input for the gasification process in the production of high-value bio-based fuels and chemicals. Another application of this fuel is in the residential or decentralized heating, where it is co-fired with coal at coal-fired power plants to produce heat. It has many different applications and usage in many different parts of the energy and sometimes material industry.
So now we're going to go over some advantages of torrefaction. Literature values for energy content have indicated that torrefied biomass has an energy content of 18 to 20 gigajoules per meter cubed. Untreated biomass has a much lower energy content than that at 10 to 11 gigajoules per meter cubed. So as you can see, torrefied biomass has a lot better heating value than untreated biomass. The torrefaction process involves boiling off a lot of water at the beginning with the drying process and through the torrefaction process. So a lot of the water is removed throughout the torrefaction process, and as a result, that lowers the moisture content, and moisture content is usually bad for torrefied biomass, or any solid fuel for that matter. So this is very helpful for biomass. And then a third point is torrefied biomass is usually easier to transport than untreated biomass, and as a result, the cost of transportation is usually cheaper for torrefied biomass. So this is also a good advantage. Torrefied biomass, with it being dried out and not very dense, is very easy to pulverize torrefied biomass, and pulverization is very beneficial for solid fuels, especially because that increases the amount of surface area per volume for solid masses, and as a result of increasing the surface area, you have much more combustibility of the fuel. So that means torrefied biomass is very easy to have very good heating value, and it can heat very efficiently. And then one last point for advantages is that torrefied biomass has been proven to emit lower amounts of noxious gases and greenhouse gases. This is always good for the environment, helps to combat global warming, and coal is known to produce a lot of noxious and greenhouse gases, so using biofuels is a much better alternative. Some of the disadvantages for torrefaction is that sometimes you need to transport biomass very far to get it to a torrefaction plant. Torrefaction is best done when executed close to the source, but sometimes the biomass has to be shipped all the way across a country, even across continents. Biomass can be shipped. And then another point is that torrefaction requires an energy input to make torrefied biomass. So part of the torrefaction process, as mentioned before, shows that a significant amount of energy is required to increase the temperature of a torrefaction process plant, and that helps with breaking down biomass into torrefied biomass. So therefore, you get a little bit lower energy return on investment when you have to input so much energy. But it is still better than using untreated biomass. And the last point for disadvantages is that production can sometimes use a lot of cooling water, so this has negative impacts on the environment. As for the economics involved with torrefied biomass production, it mainly depends on the annual capital investment and production costs. And within those two things, many of the costs are concerned with the heat duty involved, the mass flow rates throughout the system, the design of the process, and the use of power equipment to accomplish torrefaction processes. Torrefaction plants are usually capable of producing 60 kilotons in a single process. And to purchase and install the equipment for torrefaction can cost around 5.2 to 7.5 million euros to complete a single process at this capacity. And then, all things considered then, once started up and ready to go, the cost to produce torrefied biomass is usually at around 40 to 56 euros per ton of torrefied biomass. And this graph here kind of shows a comparison between wood pellets, which can be used as biomass fuel, and torrefied wood pellets, which can also be used as fuel. As you can see, it varies significantly between extracting the raw material and transporting it. But in summary, the total cost for the production and delivery of torrefied biomass is usually around 80% that of untreated biomass. So even though untreated biomass does not have as good of heating value because it doesn't undergo an energy intensive process, it still actually costs more to use and transport that than it does for torrefied biomass.
I'm Zach. I'll be talking about the environmental impacts of torrefaction and torrefied biomass production. Locally at the plants, there will be noise pollution, some dusting, and occasionally malodorous gases, so it smells bad. There are also some carbon monoxide, carbon dioxide, and NOx emissions. However, compared to coal plants and using coal for the energy production, the carbon dioxide emissions are significantly less for torrefied biomass. There's also less demand for imported energy sources to these local plants, so the local economy around the plants can be helped. In some plants, you can use the torrefaction gases created from the process to further heat the process and save costs on energy. Continuing, in some plants, water vapor is used as the inert gas instead of nitrogen. In these types of plants, the water vapor will condense into liquid water, which now will need to be treated. An estimated 400,000 liters of water condense annually in a torrefaction plant using the water vapor, which of course then all needs to be processed on its own. Torrefaction is best used when it's close to the source, so plants that are able to use torrefaction will have less transport costs and less chance that the biomass degrades before it can be enhanced. Compared to other processes that use biomass and woody plants to create energy, torrefaction has significantly higher energy output. As you'll see here, torrefaction has 94% efficiency as opposed to pelletization and fast pyrolysis. Torrefaction is also cheaper to conduct than pyrolysis. Torrefaction produces fuels with the highest energy content compared to these other processes for biomass and woody plants.
For my section of this project, I talked about the torrefied wood pellet use in existing plants. This case study was about a pilot plant that was set to be tested in Porciala, McKelvey, to study the environmental impacts and environmental risk assessment of torrefied biomass use. This case study was run by MICTEC Ltd. in Biosima Cluster, which is a bioenergy development program. Although torrefaction technology may be applied to various biomasses, this study focuses on the forest bioenergy and mainly that of wood-based fuels. This technology will be used primarily in co-firing in existing coal-fired power plants. The use of this technology is expected to make a meaningful impact on economics and in the environment. This is due to the fact that it has existing infrastructure in coal-based power plants, and this exists at a high market volume. The expected environmental impacts from this are CO2 emission reductions of up to 0.42 kilograms per kilowatt hour, and this will aid in the goal of achieving a 20% share of renewable energy sources in this region. This process has 5 major steps, the first being initial heating. Temperature rises to approximately 100 degrees Celsius, where water begins evaporation. The second is pre-drying, where temperature is kept constant until temperature begins to rise again due to excess water evaporation. Thirdly is post-drying. Post-drying is where the temperature rises to 200 degrees Celsius, where all remaining water evaporates and moisture content approaches that of zero. Fourthly is the torrefication part of this process. This is comprised of 6 main stages, where the density of the material reaches 10 to 20% lower than the other dried material. Lastly is solids cooling, where the product is cooled until the gas contains 50% water, 10% CO2, and 60% incombustible raw material. The wood pellet torrefication process has 5 main steps. First being initial heating, where temperature rises to approximately 100 degrees Celsius, where water begins evaporation. Secondly is pre-drying, where the temperature is kept constant until temperature begins to rise again due to excess water evaporation. Next is post-drying. temperature rises to 200 degrees Celsius, where all remaining water evaporates and moisture content approaches zero. Fourthly is torrefication, which is comprised of 6 main stages where the density of the raw material reaches 10 to 20% lower than dried raw material. Lastly is solids cooling, where the product is cooled until the gas contains 50% water, 10% CO2, and 40% incombustible raw material. This ends with a final fuel product. Next is how they collect this raw material and how this affects the environment. Raw materials harvested for wood pellet energy production include branches, canopies, and stumps. These are all collected from thinning sites, but primarily final felling sites. The canopy and stumps collected represent 70 to 80% of total harvesting, while small diameter wood represents the remaining 20 to 30%. The uses of these wood-based energy sources decreases the need of foreign energy sources needed, which in this situation refers to coal, which is the main fossil fuel used in this region. Certain environmental precautions are implemented in order to limit an already diminished environmental impact caused through this harvesting. Some of these include a 30% logging residue left on site due to aid in the regeneration of the ecosystem. All deadwood is preserved, and stumps are not taken from important sites in order to aid in preservation of this already flourishing ecosystem. In logging potential calculations, growth is greater than reduction in regards to the forest as its use as a carbon sink. Therefore, it will not be a threat to the utilization of this characteristic. The GHG balance is also slightly affected by this wood harvesting. The GHG balance is the estimate of the volume of greenhouse gas emissions emitted by an organization over a given period of time. Now, transportation impacts. In the scenario of the majority of wood material, it is harvested in a 60-kilometer radius from this plant. Transportation is done mainly through full and semi-trucks from the felling sites to the plant. It is found that using full trucks allows for a larger load to be carried, and thus this is more economically valuable. And the estimated CO2 emissions annually for a 50-50 split of semi and full trucks is roughly 12,000 kilograms of carbon dioxide per year, while if you use a 75-25 split of full semi trucks, it is 11,230 kilograms of CO2 per year. Now, the environmental impacts of torrefied biomass production. The environmental impacts of these plants and processes are almost exclusively through air emissions. The concentration of substances in the flue gas emitted during production are very low, thus leading to a lower environmental impact when compared to traditional power plant processes. NOx emissions are remarkably lower using the Jartek process. This process is where water is used rather than nitrogen as an inert gas during the processing. Wood products contain a lower sulfur content, which leads to lower SO2 emissions when wood material is torrefied. This pilot plant is expected to have a lower physical materials demand. Therefore, the emissions table located in the next slide actually shows slightly elevated values in what is to be expected from this pilot plant. This chart shows the emissions of the Torcoal pre-existing torrefication plant. If you can see, the CO2, NOx, and SO2 emissions are slightly higher than they should be. We expect a slight diminish due to, as previously stated, the smaller demand for physical materials.
Alright, so now we're going to discuss torrefaction and its role in the United States. In the U.S., torrefaction is picking up rapidly. And as a matter of fact, the U.S. has endowed torrefaction as exemplified by the U.S. Endowment in Forestry and Communities, the organization. This organization has provided funds towards torrefaction startups This was back in 2011, I believe, and many companies from the US and from outside the US, such as Europe, were trying to get in on the funds to help start up their torrefaction businesses. So this is an indicator showing that the US government is making an effort to make torrefaction more prevalent as a solid fuel producer. And also, torrefaction startups are starting up across many U.S. states, everywhere from coast to coast. And as I mentioned before, Europe is even getting involved with torrefaction. So taking a look at the future of torrefaction, there's a company called IEA Energy, which is a sustainability network that has analyzed torrefaction. From their analyses, they've noted that research has been rapidly increasing over the past decade for torrefaction, and as recent as, and it's pretty interesting that research has been increasing so much, because at around 2012 they state that they found many startup companies to be failing, and many were even going bankrupt. But now at least as many as 60 plants are in operation as of 2015. And this number is expected to increase in future years. So the future of torrefaction is looking bright. And here's a table that kind of goes over the future expectations for torrefaction. This table pretty much just shows the expected capacity increase for plants producing torrefied biomass. So as you can see, in 2010, it's quite a low number of metric tons, and by 2030 it should increase significantly. You can see in the added capacity row that from 2010 to 2015, only 0.5 metric tons are expected to increase, but it's expected to increase all the way by as many as 20.5 metric tons by 2030. So again, the future of torrefaction is definitely on an upward trend, and you might see more torrefied biomass being used as opposed to coal. And then this last figure also goes over torrefaction in the future. So you can see in 2015, the price to make torrefied biomass is pretty high, but as you look into the future, by 2030 the price will lower, and then the x-axis is showing the production capacity. And as I mentioned before, the production capacity is expected to increase. So again, torrefaction is trending upwards, and you should see it become a more common thing in the future. And if you haven't heard of torrefaction before this presentation, you should definitely know about it, because torrefaction definitely has a large impact on the economy, and it should be a very good alternative source of energy for the future.
Torrefied biomass is an alternative solid fuel option created by a thermochemical conversion process. Torrefied biomass is beneficial because it has better heating value than regular biomass and fewer emissions than coal does. Economically, torrefied biomass is a feasible option and even cheaper than other pre-treatment processes. Like other resources, the collection, transportation, and production of torrefied biomass has an impact on the environment. The future outlook for torrefied biomass is promising,
and it is expected to become a more prominent source of energy in the future.